I like number 17 a lot because it requires a little bit of geometry that you guys probably haven't used in about 3 years, so it might refresh our memory here just a little bit. So what's going on? We've got a man who's 1.8 meters tall, and let me just stop right here. The height of the man in question is not a variable quantity. So in terms of how tall this guy is, 1.8 meters is a fixed amount, so we don't need a variable there to represent the height of the man. That's a constant value, so let's remember that. He's walking away from a 5-meter lamppost, and that's also a fixed quantity right there. The height of the lamppost isn't changing as the guy walks further away. And he's walking away at a speed of 1.2 meters per second. And then they said find the rate at which his shadow is increasing as we're looking through this one right here. So, all right, what's going on here, guys? They were nice enough to kind of draw the picture for you right here, and they've given you two variables here, and I want to talk about what they are. X, if I were to ask you guys what that represents, is going to be the distance now from the base of the lamp, or really the lamp post, to where the man is standing right here. So X is how far the guy is from the post. And I'm going to stop right there. They tell us in the problem that the man is walking away from the lamppost at a rate of 1.2 meters per second. So that is a derivative that we were just given here, guys. X is increasing at a rate of 1.2. So we know that dx dt is 1.2 meters per second. And since the man is moving away from the lamppost, X is growing, and it makes sense that that derivative, therefore, is positive. Okay. What else then? Find the rate at which his shadow is increasing in length. So the derivative we want to know here is the derivative of the length of the man's shadow, which I'm going to do in red, is right here on the ground. The shadow of the man is on the ground, and it's on the opposite side of him from the light source. So since the light is behind him, the shadow is going to be on the ground in front of him. Y, therefore, is the length of his shadow. So they want the rate at which the shadow is changing, or it actually says increasing in the problem, which tells me the answer better be positive. So they want to know dy dt, and normally we write something at the end of this. At the moment when t equals this, or x equals this, but they didn't say anything like that within that problem. So what I've written right here, they want dy dt, seems to me anyway like a complete representation of what it is that they asked for. That tells us something, you guys. That tells us that it really doesn't matter when we're measuring this and answering this question, that the actual time-specific values of x and y are probably not relevant to solving this problem. Let's see what we can come up with. So we need an equation that eventually relates dx dt and dy dt. Well, before that, we have to relate x with y. And this is where I bet a lot of you got stuck here. How are we supposed to take a problem like this and get an equation that connects x and y? It's not a Pythagorean theorem problem because we don't know the length of the hypotenuse and we don't care about the length of the hypotenuse. What this is, guys, is a similar triangles problem. You've got one triangle here that looks like this. That would be kind of the big outer triangle there in blue. And then there's another triangle right over here in red. And what I'm hoping you guys remember from geometry, these two triangles are the same. I should probably get rid of that right there, guys. These two triangles here are the same shape, but they are different sizes. And when that happens, all right, I goofed that up. That was 1.8 meters. This is what we have here, similar triangles. And as you hopefully remember from geometry, in similar triangles, their corresponding side lengths are proportional. What do I mean by that? All right, let's look at the blue triangle. The left side of the blue triangle has a length of 5. So I'm going to start a ratio that looks like that. And the left side, the corresponding side of the red triangle right here, has a length of 1.8. Now that ratio right there, left side to left side, is going to equal the ratio of, let's go with the bottom sides. How long is the entire bottom side of the blue triangle? It's x and y put together. So x plus y is the length of the entire bottom side of the blue triangle. How long is the bottom side of the red triangle? That's going to be y all by itself. So that's using a statement of proportionality here among similar triangles to establish this relationship between x and y. Now, we could differentiate this equation right now the way it's written, but that would involve using the quotient rule over here on the right-hand side, whereas the left side is a constant, so its derivative would just be 0. That'd be really easy on the left side, but really hard and messy on the right. So let me remind you guys, you don't need my permission to do this. You can follow the rules of algebra anytime you want, and you can manipulate or reorder or rewrite an algebraic equation to suit your needs. I'm going to make this thing easier to differentiate, so I'm going to go ahead and cross-multiply this equation and get rid of the fractions. I'm going to multiply the 5 times the y, and then that's going to equal the 1.8 is now going to get distributed here and get a 1.8x plus a 1.8y. And that is much easier than what we just dealt with because now we don't have any fractions to get in the way and require the quotient rule. Actually, let's go a step further. I've got two like terms right here. Why don't I put those two together? I'll subtract this 1.8y over here to get a 3.2y is equal to a 1.8x. That's not really all that bad. And actually, if I'm looking ahead, what I'm trying to solve for right here is dy dt. That actually means, let me move up here, guys, it would be even easier if we could isolate this y here, which I'm going to do by dividing by 3.2. So we're going to get y is equal to a 1.8 divided by 3.2 and then multiplied by x. Now that 1.8 over 3.2 simplifies to something, probably 9 over 16. I don't really care that much. Okay, I can leave the decimals right there. So now I think it's time to go ahead and differentiate both sides. The derivative of y with respect to t is just dy dt. On the right side, we have a linear function. It's some coefficient times x. And the derivative of any linear function is just its coefficient, which in this case is 1.8 over 3.2. And then we're going to multiply that by the derivative of x with respect to t. And what I want you guys to notice right here is that this derivative equation that we just came up with right here only has two variable quantities, dy dt, which is the one that we are trying to find, and dx dt, which is the one that they gave us. But you'll notice there is no x, there is no y in this equation. And back to what I said before, they didn't have to tell you when to measure dy dt, not at a specific value of x or y or h or time or anything like that, because it doesn't really matter how far the guy is away from the lamppost to answer this question. So we're going to get here a dy dt is equal to a 1.8 over a 3.2 multiplied by dx dt, which is a 1.2, and I don't think I know that answer in my head. So dy dt is equal to, let's see if I can remember this now. Here we go. We had a 1.8 and then divided by a 3.2 and then multiplied by a 1.2 should get us our answer here of 0.675. So 0.675. Every rate here, velocity was measured in meters per second. And that's going to be our answer there, guys, for problem number 17.